Hello students, in this video you will understand about the stereoisomerism, which is a major category of isomerism in coordination compounds. In my last video, I gave you clear description about one of the major category of isomerism within coordination compound, and that was structural isomerism. So let us start with stereoisomerism. Here the first type of isomerism is geometrical isomerism. In case of geometrical isomerism, the ligands occupy different positions around the central ion. So these ligands can be either adjacent to one another, like in this case, right? So the ligands like amine here are adjacent to one another, which will be called as cis isomer, or the ligands can be opposite to one another, like in the other case. So amine ligands are opposite to each other. This will be called as the trans isomer. So geometrical isomerism is often referred to as cis-trans isomerism. Now this geometrical isomerism we would consider in complexes of coordination number 4 and that of coordination number 6. As far as coordination number 4 is concerned, it can adopt two type of geometry. One is tetrahedral and the other is square planar. As far as the tetrahedral complexes are concerned, in that case all the positions or all the ligands are adjacent to one another around the central metal ion. Because of this, you cannot differentiate between cis or trans isomer. So in short, we can say geometrical isomerism does not exist for tetrahedral complexes. However, it is very commonly seen in case of square planar complexes. As you can see here, so the ligands consider in the form of the positions around the metal ion 1, 2, 3 and 4. So if these positions are adjacent to each other, which are the cis positions here? So 1, 2, this would be a cis isomer, or the other possibility 2, 3, a cis isomer, then 3, 4, a cis isomer, and the next possibility 4, 1, a cis isomer, right? On the other side, the opposite ones will be producing a trans isomer. So 3, 1 will be a trans isomer, or if the ligands are present, the same ligands are present on 4 and 2 sides, then those will be trans isomer. Next we will consider about the complexes of coordination number 6. Coordination number 6 tend to show a geometry of octahedral arrangement. So in this case, we can just quote the positions as on the screen. So metal ion surrounded by 6 ligands, whereby you can consider that position number 2, 3, 4, 5 is a part of a square planar arrangement, and 1 position is above this plane and 6 position is, say for instance, below the plane. I hope octahedral arrangement is clear, right? Now which are the cis isomers in case of octahedral arrangement? So consider this 2, 3 cis arrangement, then 3, 4 a cis arrangement, next is 4, 5 cis arrangement, then 5, 2 cis arrangement. Okay, then next you can consider this one position which is above the plane in corresponding to 2 a cis isomer again, then 1, 3 again a cis isomer, again 1, 5 a cis isomer, 1, 4 a cis isomer. Similarly, you can consider this position 6 with reference to 3, it will be cis, 6 with reference to 2 will be cis, 6 with reference to 4 will be cis, and 6 with reference to 5 will also be a cis isomer. As far as the trans isomers are concerned here, so you have to consider the opposite positions. So which are the probable opposite positions here? 1, 6. So if the common ligands are present across these positions, then it will be a trans isomer, or if they are present at 2, 4 positions, that will be a trans isomer, or if they are present at 3, 5 positions, then that will be a trans isomer, right? I hope you are clear up to here. Now move ahead. Now this is a special type of isomerism observed in octahedral complexes, that is complexes having coordination number 6 of the type Ma3B3, right, where A is one type of ligand as you can observe here, and B is another type of ligand, right? Now in such cases, there is a special type of isomers observed called as facial isomers, often denoted as FAC isomers, or the other type isomer is meridional isomer, represented as MER isomers. Okay. Now how will you differentiate between this? What are facial isomers? When the three identical ligands are present at the corners of a triangular face of an octahedron. So you can observe this octahedron, right? Now this is a triangular face which I have shaded for you so that it can be clear to you. So if the identical ligands are present at the corners of a triangular face of an octahedron, then the isomer is termed as facial isomer, right? About meridional isomer, when the three identical ligands are present at the corners of a square plane. So this is a square plane arrangement here, right? Within this square plane, you have to consider the identical ligands. So these are the identical ligands, and they are present at the corners of a square plane, right? In the form of a in the form of a triangular arrangement. So that will be called as a meridional isomer. Is it okay? So that's about the complete explanation of geometrical that's the complete explanation about the geometrical isomerism in case of stereoisomerism. Next we'll move on the other subcategory of this, that is the optical isomerism. The isomers which rotate the plane of polarized light equally but in opposite direction are called optically active isomers. So the isomer which rotates the plane of polarized light to the right is called as dextrorotatory, and which rotates the plane of polarized light to the left is called as leorotatory, right? Now further, within a mixture or within a solution, both of the isomers can exist in equal proportion, and that will be called as racemic mixture. In case of racemic mixture, it will become optically inactive. Is it okay? So now we can say, in case of solutions which contain equal concentrations of the two isomers, what will happen in this case? The rotations by the two isomers will cancel each other, right? And this particular racemic mixture will not have a tendency to rotate a plane of polarized light, and so it is optically inactive. So there are basically two conditions to observe whether optical isomerism is possible or not. The first condition you need to take a note is there should not be a plane of symmetry within the molecule, and the second condition is it should possess non-superimposable mirror images. Both the conditions would be clear to you with the help of an example which I'll be covering in the other part of the video. Let us see. In case of coordination number 4, we have two types of geometries, tetrahedral and square planar. In case of square planar complexes, what you can observe here, it has a plane of symmetry. That means you can create a clear mirror images of each other. This plane of symmetry can be in this way, this plane of symmetry can be in this way, right? Or even in this way. So on that basis, you can say that in case of square planar complexes, optical activity is not possible. So they do not possess optically active isomers, right? However, there is a probability in certain cases, certain square planar complexes. Say for example, the ligands which are attached are different. Say here there is a phenyl group attached, right? And on the other side there is a methyl group attached. So in such cases there is no plane of symmetry. They do not have a plane of symmetry within their molecule, and such square planar complexes will have tendency to exhibit optical isomerism. However, in case of tetrahedral complexes, all the four groups are adjacent to each other. On that basis, I can say there is no plane of symmetry in their molecules, and so these tetrahedral complexes are always optically active. One of such tetrahedral complexes is been shown on your screen in the form of an example. So the first thing you need to observe, you have to follow both the instructions. What was the first condition? There should not be a plane of symmetry. How are you going to check? Consider a mirror passing through the center of the molecule. Are you getting the clear reflections of each other? No. This is a short ring and this is a larger ring. So you are not getting a clear reflections, right? That means it does not has a plane of symmetry. So your first condition is fulfilled. Second condition is it should have non-superimposable mirror images. Just check it out on your screen. So this green line which is specified here, this is a mirror, and so you are having that mirror images of the molecule. Now just consider a piece of cake you are taking which is in the form of a mirror image, and you have to place it on a plate. Let us say this left part of your molecule is a plate and the right part of your molecule, which is a mirror image of the same molecule, is a piece of cake. Just for your understanding, say this is 1 and this terminal is 2. Similarly, this is 1 here and this terminal is 2. Now you have to take or make it 1 prime and 2 prime here. So you have to take down the second portion, the mirror image, and place it over this portion. So you will be keeping it in your plate. What will happen? You can observe here your 1 and 1 prime coincides with each other. Similarly, 2 and 2 prime coincide with each other, right? On that basis, you have to check whether both the images are non-superimposable. Yes. What will happen? In this case, your shorter ring is coinciding with the longer ring or the larger portion of the ring, and this portion of the molecule coincides with the shorter portion of the molecule. So they are having a clear non-superimposable mirror images. So your second condition of optical activity is also fulfilled in this case. So on that basis we can say that beryllium complex of this type, which are tetrahedral in nature, have the tendency to show optically active isomers. Now let's move ahead. Next, let us consider octahedral complexes, coordination number 6 of the type M, AA2, B2. Now this AA is a specified symbol for symmetrical bidentate ligands, and B2 means we are taking one type of ligand which is different from this ligand and two groups of this, right? So that is an example I am taking here for rhodium complexes. Rhodium, 2 molecules of ethylene diamine and 2 groups of chlorine, right? So as it is shown, it has a tendency to show geometrical isomerism. So it has cis form. This is the cis form of the complex and this is the trans form of the complex. Now this, one more thing to specify here, this AA, why it is called as symmetrical bidentate ligand? Because these are the ligands which have 2 dents and both the dents are same. So if you consider ethylene diamine, in case of ethylene diamine you have 2 dents, nitrogen on one side, nitrogen on the other side. So both the dents are same. So they are called as symmetrical bidentate ligands. I hope you are clear. Okay. Now let us consider, are both the forms optically active or not? If we consider cis form of this particular complex, check for its mirror image, right? So this is the mirror image of this complex. You are going to do it in the same way. Cut the piece of the cake as its mirror image, put it over a plate, check whether it is producing a non-superimposable mirror image. Yes, it is producing a non-superimposable mirror image. So on that basis I can say cis form of this complex is optically active. Is it okay? Now consider the trans form. If you are taking the mirror image of this trans form, just imagine, so this is the ethylene diamine portion, this side mirror image, this is the other side, right? And rhodium in the center, chlorine here. Now just cut this piece, put it over the plate. What will happen? Is it producing a non-superimposable mirror image? No. Both will be exactly resembling each other. So no non-superimposable mirror images are produced in this case. That means I can say transform is optically inactive. Is it okay? So that is the complete explanation of stereoisomerism. Then in my next video, I'll clear you some questions regarding the entrance examinations related to this isomerism concept. Till then, you watch my both the initial videos of isomerism, make your topic clear so that you will be ready to attempt the questions for isomerism in the form it appears in your exam. So work hard, stay safe.